So we have here a step input mechanical power delta B, and this is the response of the rotor angle, and this is the response of the rotor speed omega of t. And you can see here the that is oscillatory. We have here sine, the function of time, so we have an oscillatory response. The response time constant tau is usually the 1 over sigma, which is the root of the characteristic equation of lambda equal to sigma plus j omega. So 1 over sigma gives you the time constant, and for time constant, it is approximately the settling time. Okay, so let us take this example and analyze the steady state stability of the system. Let me first, we need to close this subject. I don't know who still not selected the topic. We have only 9 and 10 is remaining. We need one student in 10, and the 2 will be together in 9. So please, for those, and I think 3 students not yet decided, immediately after the class, please send me either 9 or 10. We need to close this subject. Okay. So a 60 Hertz synchronous generator having inertia constant H equal to 9.94 megajoule over megavolt ampere, and is second. Okay. This is second. And the transient reactance XD prime is connected to an infinite bus. The machine is connected to an infinite bus, as shown in the figure below. Reactances marked on the figure are given in per unit on a common system base. And we don't need to change the per unit quantities. The generator is delivering a real power of 0.6 per unit at 0.8 power factor lagging. Okay, so the power factor is 0.8 lagging to the infinite bus at a voltage V equal to 1 per unit. Assume this 1 per unit infinite bus voltage. Assume the per unit damping power coefficient is D is 0.138. This is D appears in swing equation. So you have here H over pi F0 d square delta by dt square equal to P mechanical minus P electrical, which is B max sine delta minus D delta by dt. So this is D, which is point, and we consider here the damping. The cases that we already considered before, we are considering here there is a damping coefficient here. So definitely, how to tackle the problem? What would be the first step? Can anybody tell us what is the first step in this problem? Raise your hand if you want to answer. Okay, so who is raising his hand? Ayub Al-Hurani?
Doctor, I think the first thing we need to find the E prime.
E prime. E prime, yes, we need to find the E prime magnitude and angle, delta. So we need the rotor angle, the initial rotor angle, and we need the magnitude of E prime. How can we calculate this? We have the initial real power delivered, and we have the power factor here, and we have here V equal to 1 per unit. Okay, so we have here this angle 0. We usually assume the infinite bus voltage as an angle 0. Okay, obtain the equations describing the motion of the rotor angle and generator frequency. Rotor angle and generator frequency, delta and F. F or omega, doesn't matter. Omega equal to 2 by F, whatever. So in the following cases, if we have a small change of delta equal to 10 degrees, and this is what? Zero input or zero state response. If we have a small change of delta equal to 10 degrees. So this is zero input. There is no change in mechanical power. The change here is in the state. Here we have the mechanical power change equal to 0.2 per unit. A small change of 0.2 per unit, but this is zero state response. Okay, so what we need is to have delta of t, how much, function of time, and also f of t, which is omega of t. Okay, so what do you think? You have here V infinity given, reactances, and XT, transformer impedance, and also the transient reactance of the machine. So, and you have here the delivered power, V equal to 0.6 per unit. So what do you think? Can we get the E? Can we get the delta 0? Do we have missing information? Or this is enough? Reactance is marked in the per unit, and the common is the generator is delivering a real power of 0.6 per unit with 0.8 power factor lagging. And you have here the S quantity, S as a complex number. You have the real power and also the 0.8 power factor lagging. So you can get the complete S as a magnitude and angle. And you can have, this is S. We have here 0.8 power factor lagging, and the power B equal to 0.6. So S, and you have this angle, cosine theta equal to 0.6 over S, this is equal to 0.8. So you can have S, and you can write S as with the angle equal to theta. So the magnitude and the angle of the complex power is given. And if you have the voltage here, so with this complex power and the voltage, you can get the current. And if you have the current, you can combine all the reactances, and with the current, you can get the E prime, which is magnitude and angle. And then we can proceed from there. So the transfer reactance between this and that equal to 0.65. The per unit apparent power is is equal to 0.6 over 0.8 with angle cosine inverse 0.8 power factor lagging, so the angle is positive here and the lagging power factor. So this is S. With this S and V, you can get the current. And S equal to VI conjugate, so I equal to S conjugate V conjugate. And voltage is 1 with angle 0, infinite bus. This is S conjugate, and you can get the current. And with this reactance, with the current, you can get the E prime equal to V plus JXI, and this is the current here. So you can get it as 1.35 and 16.79 degree. So this is the E prime in per unit, magnitude and angle. Okay. So this is BE max equal to E prime V over X. We can calculate it definitely. You can have it. Thus, the initial operating angle is 16.79 degree, which is 0.2931 in radian. Just 1 pi over 180. So the synchronizing power coefficient. How much is the synchronizing power coefficient? Vs equal what? Equal to B max cosine delta 0. So if this is delta 0 and the B max is known, the E prime is known, V over X. So you can write BE max cosine theta 0 or delta 0. So this is the synchronizing power coefficient. And of course, you can get the omega n, which is the square root of this. We already derived this before. This is omega n by F0 H over Bs. So you can write here the omega n. Omega n is the natural frequency of the oscillation. Zeta equal to d over 2 square root of this. So you can calculate the damping. And we are just substituting in this equation that we derived earlier. And if you can derive it easily, and you can derive these equations easily. As we mentioned, we have at the beginning H over pi F0. You have here S square delta or delta of S, delta of S, the d square by dt square equal to, there is no change in B mechanical. And we have here this B max. If we write the swing equation, H over pi F0 d square delta by dt square equal to Pm minus B max sine delta minus d delta by dt. And you have here this, if you have this delta equal to delta plus delta, and you expand this sine delta, cosine delta equal to 1, the sine delta will go together, and you have here minus B max cosine delta 0 delta plus delta of S طبعا, and you have here minus D S delta of S. So you can have all this in the, and you can get the characteristic equation, and you can kill the roots, or you can write the characteristic equation in standard form: S square plus 2 zeta omega n S plus omega n square equal to 0. If you write this in this standard form, you can easily see what is omega n, what is zeta, and so on. So you can easily derive these forms. Okay, so omega d is omega d equal to omega n square root of 1 minus zeta square. So this is the damped frequency of oscillation, and this is natural frequency of oscillation. Do you have any question? Right, now if we have delta delta, a steady change in the state 10 degrees, which is equal to 0.1746. Usually when we substitute on delta delta in any of these forms, we use, of course, we use in radian طبعا. We are not using the yes, for this one, when you substitute this, you substitute in radian. So you have delta delta 0 equal to 0.17. Okay, so this is omega d, and you can substitute directly in this formula. Delta equal to delta 0, the initial angle, plus the change in the angle, square root of 1 minus zeta square e to the, and so on. So all the quantities are known, and also this formula, all the quantities are known. This is all, you can, of course, write F equal to omega by 2 pi. So you can have the frequency of oscillation. Substituting, so you end up with delta equal to the angle, the initial angle, which is 16.79, 10 to the minus sign as such. And you can also write the frequency equal to the initial frequency, which is 60 hertz, and minus omega n. All this you can have them as such. So this is the delta and the frequency due to the stable change in the state. Okay? Are you following? If you have any question, please raise your hand. The system response is shown as, of course, you can plot delta of t. You can have the angle, the initial angle. Ahmad Sulaiman. Ahmad.
Yes, Dr.
Yes, please.
Repeat the last part.
The last part.
Yes, the previous slide.
This one?
Yes, doctor.
This is just substitute here in these two formulas, which is derived earlier. Okay? And this is delta 0. Delta 0, it was initially, of course, this is the initial angle. We calculated from the steady state condition. It was like 17 degrees or something like this. Delta 0, which is the stable change here. Zeta is already calculated before. Omega n, omega d, theta, which is cosine inverse zeta. You can have this angle. This is theta, which is cosine inverse zeta. Is it clear?
Yeah, it's clear.
And this is the frequency, initial frequency is 60 hertz, the steady state, which is corresponding to omega 0. And of course, you can have here this omega also over 2 pi, so it becomes Fn, and you can continue, and you can just substitute, you'll end up with this. So you can draw these responses. Delta as a function of time, you have it here, and if you can start with t equal to 0, 0.1, 0.2, 0.3 second, and so on. So you end up with the following response. So the initial value was 17, like here. This is the initial delta 0. we have a step change here in the angle, which is 10 degrees. And this is the response. And the angle will be back to its initial value. Okay. طبعا we have damping. We expect this response actually. We expect the response to be stable, and we have zeta equal to 0.21 something. So we have positive damping, so the system is stable. So we assume, or we expect that the oscillation will die out after some time. So this is delta 0 and this is F0, starting from 60 hertz initial, and then the frequency is oscillating as such. Of course, at the end it will back to 60 hertz. Okay. طيب عمر Salman.
Yes, Umar Salman. Doctor, yes, apart from the fact that we can obtain the graphs from this, we can obtain these plots. What is the significance of those equations? I mean, the damping equation. What's the significance of those equations?
These equations?
Yes.
This is the response.
This response, the last two response equations like this.
These are the responses.
Yes.
Okay. So if you have, of course, from here you can check whether the system is stable or not. طبعا zeta is positive. This is 1. Also for this exponent, if this exponent is negative, that means it will die out with time. As t goes to infinity, this becomes 0. This part becomes 0. So the system is stable. And also this exponent is the same, negative. That means, if this exponent is positive, then it increases with time and the system becomes unstable. This is the analytical solution. And we here in these curves, we just plot this solution, ya Salman. And we plot this solution based on this solution. And we plot these curves based on this solution, analytical solution. Okay?
Yes.
So, these equations are, the basic, and then we can illustrate it as the figures here.
Yeah, Doctor, what I'm trying to ask is maybe somewhere maybe it could be used in modeling, maybe equations like this. For example, with those equations, I know we can find we can differentiate the equation, we can integrate. So can we say we can find? Does it mean is the equation used in modeling somewhere? Maybe where we can find minimum point or maximum or something. I mean, this is where I'm trying to ask if the equations like this is used in modeling in power system.
I didn't get your point, Salman. With this equation, what do you want to say?
Yeah, what I'm saying is that, for example, in the power angle equation, now this particular equation that we obtained, if Mathalan we decide to say let us differentiate this equation.
Differentiate?
Yes, maybe with respect to our time.
Why? Why you want to differentiate them? Differentiate these equations. What is the significance of this step? What do you want to say?
Okay, what I want to say is that if you differentiate the equation, for example, and then we find the turning point, say at the differential equals to 0, then we will obtain some values of time at which maybe the power angles will be equal to 0 or some minimum point or maximum point. So in such a case, and same thing for the frequency as well. So can this be significant in modeling or something? This is what I'm trying to ask.
No, actually, this is not important. Usually this is not important to get the maximum or minimum value. Maybe if you want to get the maximum overshot and the minimum undershot, or the if you differentiation will give you this minimum point and the maximum point, minimum point and maximum point. So you will get these points. So are these points are significant? It could be if you want to calculate these overshot. Okay, if you want to calculate this, you know the initial value, and if you substitute back after getting this time, you can substitute with the so you can get this undershot or overshot here and the undershot here and so on. But this will not give you any important information that you can build on and the procedure. Okay. You can, of course, get the minimum value, maximum value, and you can see the overshot and undershot. But this is extra work. If you have something in your mind that you can build on these values other than getting the overshot and the undershot, this could be done. No problem.
Thank you, Doctor.
Okay. So let us continue for the second case, which is the zero state response, where you have here the step change in the power. So we derived this case earlier, and we know that this is delta and this is omega, or frequency. So this is delta 0. Do you think this is delta 0 in the previous one? What is delta 0 here? When we derive this, do we have something wrong in this equation? It is 1. It is 1 here. This is 1. And delta 0 is 0. We don't have change in the state. So this is definitely wrong. So this is 1, not delta 0. Let's copy paste. Sorry for this. So this is delta, the initial value, and this is the speed, and of course you can get, just substitute delta b equal to 0.2 f0 h omega n. The omega n is already calculated, the zeta is already calculated, and the omega d is already calculated. All these already calculated, doesn't change. These are the characteristic of the system. So it doesn't change whether you have a zero state or zero input. All these time domain response characteristics or properties are fixed. So delta equal to this, you can have it here, and also the frequency, you can write it here, and we expect, of course, the system to be stable, and we have the zeta, and we have this also is negative. So the system response is as shown here. Here you can see that the angle starts from delta 0. So there is no change in the angle, but the angle starts from here. if you look, go back to the to zero input response, the angle starts from 10 degrees more, which is the step size. So this is the angle, and we expect, of course, that when we increase the B mechanical, the delta will increase. So we start from here, but we end to a different angle, which corresponding to B mechanical equal to B mechanical 0. This is equal to B mechanical 0 plus 0.2. So we have a step change in the mechanical power. And if we have a step change in mechanical power, then we are talking about higher angle. So this is delta 0 and this is delta final. And this is 0.2 step. So we expected the angle to be, of course, higher, but the frequency is fixed. Definitely the frequency should remain at 60 hertz. Okay. Any question, Ayub Khalifa? Ayub?
Yes. Regarding to the theta, why you consider it 77.7 and in the calculation it's 36?
Again?
Theta in the equation, in the delta equation, sine 60 plus 77.7. Yes, this value. The theta is 36, right? Because you calculated in the beginning, once you calculate the apparent power.
Oh, okay. This is not the bar, this is not the phase angle. This is the phase angle. This is
this theta, right?
No, this is the phase angle. This is between voltage and the current.
Yes, and usually represented by theta, right? Or
No, this is phi, let us say. This is different angle. That angle, theta, that angle is you have here for the roots of the characteristic equation. These are the characteristic equation, and this is the angle theta. This is the angle theta. This is one root of characteristic equation. This is second root. So this is the angle theta. Angle theta is cosine inverse zeta, and we calculated zeta as 0.2 here. This is zeta. Zeta is 0.2. If you get cosine inverse 0.2131, check it. If you have a calculator, check cosine inverse 0.2131.
Yes, it's 77.7. Yes.
Okay, so this is the theta. The theta here is this angle. It is not the phase angle between voltage and the current. Okay.
Okay. Clear.
So this is theta. Any other question? Okay, so this is an assignment. Develop a computer program to solve the given example and simulate the swing equation in both cases. In both cases, zero state, zero input. We need delta of t. This is the solution of the swing equation. Delta of t versus time. Okay. So you can easily develop such MATLAB code, and you can plot this equation. Okay. So by this we finish this part of the steady state stability analysis. Okay. Okay. Let us start this part, which is the equal area criteria. You already exposed to the equal area criteria as the solution, as a graphical solution of the swing equation. Here we will go over it quickly, and we will go through it in the context of a solution of the swing equation. And then we will go, this is a graphical solution, and we have later next to this the numerical solution of the swing equation. So we will not spend much time in this part, and it's already covered in 520. So introduction to equal area criteria, some assumptions. When you have this equal area criteria solution, you have to put some assumptions. Equal area criteria under sudden change of mechanical power. We will discuss different cases. If we have sudden change in mechanical power, and also if we have fault, sudden fault, and this fault could be three-phase fault or single line to ground fault, and also the location of the fault will, of course, has a great impact on the system response. Fault occurs at a pass, and fault occurs at the midpoint of the line. Where is the fault location? This is very important in transient stability analysis. طبعا we are handling now the transient stability analysis. The change here is big and sudden. So this is the in the context of, as we mentioned, transient stability analysis or solving the swing equation. We are not linearizing as we did in the steady state stability analysis. The fault type and location, different fault type and location, and also we will see a very important piece of information, especially for the protection people, which is a critical clearing time. This is very important, the critical clearing time. So we will see how to calculate the critical clearing time based on the equal area criteria. In some cases, but in other cases, of course, you have to go to a numerical integration in order to get the critical clearing time or critical clearing angle. Okay, so the transient stability studies involve the determination of whether or not the synchronism is maintained after the machine has been subjected to severe disturbance. If you still remember, when we talk about the steady state stability, transient stability, dynamic stability, the idea behind the classification of these stability types is severity of disturbance, and also the time frame. So these are the basis of having transient stability, steady state stability, and dynamic stability. For steady state stability, as we mentioned earlier, we have the small and the gradual change. So we can linearize the model, and we can have it easily with algebraic equations. Also, the time frame is not an issue. You have very long time to study the system. For transient stability, here the change of disturbance is severe, big and sudden. So we cannot linearize the equation. We have to solve the swing equation as it is, as a nonlinear differential equation. So one way to solve it is the equal area criteria graphical solution, and we will discuss later the numerical solution of the swing equation. The time frame here is a few milliseconds after the disturbance. You can say 1 or 2 cycle, 1 to 2 cycle after the disturbance. يعني بنتكلم عن 16.67 millisecond cycle. So you are talking about very small time after the disturbance. And the dynamic stability, we will see it later when we have, in between, and the time frame could reach to 5 seconds or something like this. We will discuss it later on, inshallah. So for transient stability, the system is subjected to severe disturbance, severe and sudden application or loss, sudden application of load or sudden loss of load. Both will disturb the system. And don't expect to know if we lose the load, this will be something which is easier than application of the load. And this loss of load could also create some instability in the system. Loss of generation is very severe disturbance. If you lose one generator, generation plant, fault on the system, if you have three-phase fault or even single line to ground fault, sometimes the single line to ground fault is more severe than the three-phase fault in some cases. So fault on the system. And most disturbances, the oscillations are of such magnitude that linearization is not permissible, and the nonlinear swing equation must be solved. One method for solving the swing equation is equal area criteria. This method is based on graphical interpretation of the energy stored in the rotating mass as an aid to determine if the machine maintains its stability after the disturbance. So you are analyzing here the kinetic energy stored in the generator rotor. You have here the generator. You have mechanical power input and electrical power output, and you have the swing equation, the acceleration power equal to Bm minus Pe. So you are analyzing this. If Bm is higher than Be, so the kinetic energy will increase here, and this is equal to Gd square delta by dt square. Trying to convert this to M and to H and so on. But this is anyway, you have here H over by F0, no problem. So this is the acceleration. So if we have Bm greater than Be, so the system will accelerate. So the kinetic energy will go up and the speed will go up, frequency will go up. And if the opposite, then you have a deceleration. So you have acceleration area and deceleration area. And the criteria is to have both are equal. Equal area criteria gives a quick prediction of stability. However, this method is applicable only for a single machine infinite bus or a two-machine system. And this is the limitation of the equal area criteria. It is used only for a single machine infinite bus. And this is valid only for single machine infinite bus. Usually, when you want to implement this on multi-machine system, you consider other machines as infinite bus, and you focus on a certain generator that you want to check its response. And of course, this is some kind of approximation, and again, you neglect all the interaction among the generators in this case. So this is the limitation of equal area criteria, only on single machine infinite bus. Of course, if you go in literature and you read, if you want to dig down at this point, you can go and see some efforts to generalize the equal area criteria to be implemented on multi-machine system. There are some attempts in the literature. If you are interested in, you can go and see. So assumptions, of course, analysis. Usually in our course, we will consider BM doesn't change during the swing. During this swing, I know the swing is very, very fast. This is mechanical loop, and it takes long time to change the BM. So in this case, we consider BM as constant. BE can be obtained from the steady state solution of the system, okay, which is BE equal to BM in this case at steady state. I think this is BM. I think this is BM. BM can be obtained from a steady state solution of the system. If you know that the generator delivers 1 per unit, so at steady state, your BM equal to 1 per unit. Damping powers are negligible, and this is a conservative assumption. And if we have damping, that would be okay, better. So if we neglect damping, that means we are dealing with the worst case scenario. So if the system is stable under the worst case, but definitely if we consider the damping, the picture will be better. Machines are represented by subtransient reactance. And we are talking about transient stability few milliseconds. So this will be represented by subtransient reactance, which is XD double prime here. Okay. So these are the assumptions to analyze the equal area criteria. Okay, let us consider this. We will consider some illustrative examples to address if we have sudden change in mechanical power, if we have a fault, and the fault could be three-phase single line to ground at a certain bus or at the midpoint of the line or here and there. So we will address all these issues in terms of these examples. We have 5 examples to address all these cases. For one machine, infinite bus system, if a sudden change in B mechanical, find the conditions for stability. I received a reminder for prayer. So should we stop for 5 minutes for prayer and come back?
Yes, please.
Okay. Well, let us stop here for 5 minutes. It's 6:10 now. So we will be back for at 6:10, inshallah, 6:15. And we have a quiz. So, after the prayer, inshallah, we'll see. Okay. Okay. Assalamu alaikum. Okay. Let us see this example. If we have step change in BM and mechanical power, find the conditions for stability using this equal area criteria. So this is BE versus delta. Sinusoidal, you have it here. We have at the beginning B mechanical 1. So the system is operating here. And if we increase B mechanical, so we have BM2. So this is BM2. How the system will respond, and what are the conditions for stability? Of course, we increase the B mechanical. So the system was here at the beginning. And eventually the system will stay here if it is stable, of course. So when we increase the mechanical power, we have B mechanical power here. BM2 is greater than B electrical. So this is B electrical, the curve here. So we have acceleration. And definitely the machine will start, the angle will start increasing. If we increase the mechanical, and the speed also will start increasing. And due to the inertia, the system will not stop here, it will continue. Due to the inertia, it will continue. Once it crosses this B mechanical 2, we have B electrical greater than B mechanical. So the system will start to decelerate, and assume that at this point it will reverse its direction back to this. Again, when it reaches this one, it will continue due to the inertia, and then we have acceleration, and then we have deceleration, acceleration, and so on. Usually they draw this as such. If you have this as a time, this is delta, and if you have this as a time, you will see we will start here with this angle, and then the angle will increase, and then will decrease, will increase, decrease, until it, this is similar to what we have usually draw here. This one, this is delta 0, and this is delta M, maximum angle here. This is a maximum angle, and this is delta S, steady state. Okay, delta S is somewhere here. So this is the scenario. So we have two areas here: acceleration area, area 1, and deceleration area, area 2. If the condition for the system to be stable in A1 equal to A2. So we can, of course, get the area under the curve by integration of B mechanical. We can get the area of this rectangle minus the area under the B max sine delta, integrating from delta 0 to delta S. And also the deceleration area, we can have the area under the curve minus the area of this rectangle, which be M2 times delta M minus delta S. So, and we can have the condition. طيب, assume that we solve the problem. We have A1 and A2, A1 and A2. What is the unknown quantity here? If we have A1 and A2, what is the unknown quantity that we need to check in order to judge whether the system is stable or not? What do you think?
Angle.
Which angle? We have different angles here.
Okay. Delta S.
Delta S is known.
Delta M.
Delta M. You say
yes.
when we have this condition, we will see delta M, how much delta M, and we will see based on this delta M, maximum angle here, we can check whether the system is stable or not. إنما delta 0 is known, لأنك أنت you know BM1 and you know the curve here. This is B max sine delta. So you have equal to BM1, so you can get the angle corresponding to this one. You have BM2 is known, so you can have BM2 equal to B max sine delta, so you can get delta 0 and delta S are known. So what is missing that we need to get is delta M. So what is the condition for the system to be stable? خلاص, already assume that and we have delta M, we get delta M. How can we judge whether the system is stable or not? Ayub Al-Hurani?
Doctor, to decelerate back.
I couldn't hear you, Ayub.
To decelerate back, Doctor, mean B electric, B mechanical should be higher than B mechanical.
Yes, well, this is when we have A1 equal to A2, and the acceleration area with the deceleration area, right? Delta 0 is known, delta S is known. And if we equate A1 equal to A2, we can get delta M, how much delta M, okay? So the output of these equations, A1 equal to A2, and we can say no, a system will be stable if A1 equal to A2. The acceleration equal to deceleration. Am I right?
Yes, Doctor. But
A2,
yeah.
A2 is a function of delta M. And A2 is a function of delta M. So from this equation, we can get delta M. My question is, if you have delta M, if you get delta M, can you judge whether the system will be stable or not? Salman?
Yes, Doctor. Okay, yes, I was going to say that one of the points to check to know, I mean, that would let us know if the system is stable, is that the equilibrium point, I mean, the new operating point should move back to point B.
Yes, okay.
Yes. So if we're able to obtain data M, and provided that the value of data M is less than 90, I think that will tell us that the system is likely going to be stable.
Yani what you want to say, no, if delta M less than 90, when we solve this equation, A1, delta 0 with delta S are known, for A1 can be calculated.
Yes.
Delta A2 is a function of delta M, right?
Yes.
So based on this, we can get a delta M.
Yes.
What we are saying, if delta M that we have it here less than 90, system becomes stable.
Yes.
This is what you want to say.
Yes.
Any other opinion? Abu Bakr رفع ايده ونزلها تاني. طيب. Any other?
I think we must compare with the critical clearing angle, delta M with
Delta
M with critical clearing angle.
Delta M.
Yes.
With the critical clearing angle.
Yes.
What is the critical clearing angle? طيب Ayub Al-Hurani, do you have any?
So, Doctor, delta M should be less than delta max.
Delta M should be less than delta max. So it has nothing to do with 90? You want to say that?
Yes, because in all cases, even if it exceeds 90, it will decelerate back. But if exceeded the delta max, it will accelerate.
Okay, يعني الدلتا M in principle واعتقد انه the same question you asked me before Ayub about delta.
Yes.
That it could reach higher than 90
Yes,
during
exactly.
the oscillation or not. And the answer was yes.
Yes.
Delta could go beyond the 90 degrees and it come back oscillation. And you can have with this delta, you can have this angle higher than 90, but it shouldn't exceed delta max. It shouldn't exceed delta max. Why? And this delta is 90 is wrong. We can have a delta max. Delta max is 180 minus delta S. 180 minus delta S. This is delta max. Delta S is known, so delta max is known. So if delta M, when we solve here, if delta M is less than delta max, the system becomes stable. It has nothing to do with 90. 90 when we are checking the steady state stability. Okay, the operating point. Now during the transient, the angle could go beyond 90. طيب, the question is here, and do we have, assume that we have acceleration area here. Do we have enough deceleration area to compensate for the acceleration or not? The maximum deceleration area that you can have where you have B electrical greater than B mechanical. This is B mechanical and this is B electrical. And all this area is a deceleration area. All these areas are deceleration area. So in this case, definitely delta M can go up to delta max. If delta M is greater than delta max, so that means you have here acceleration. So the system becomes unstable here. And you don't have enough deceleration area to compensate the acceleration. And at this point, the area becomes acceleration here. This is the BM and this is BE. So you have here another acceleration area, this acceleration area here. So this will make the system worse and worse. So we will get delta M and we will compare delta M with delta max. If it's below delta max, then the system is stable. If it's greater than delta max, then the system becomes unstable. I hope you know this is clear. Okay. So Saad Ahmed.
Yes, Doctor. Doctor, can you please explain in which case will both the areas not be equal?
Okay. Assume that we have such case. Okay. This is BM1. This is BM2. This is the acceleration, right? And this is the whole deceleration area available. This is A2. This is the whole area available for the deceleration, right? Is it clear? So
yes.
In this case, you have acceleration areas very high and you don't have enough deceleration area to compensate this one. That means that the system will be unstable and you have here this delta is greater than delta max. This is delta max here and this is delta S. Am I right?
Yes, Doctor.
In some cases, if this step change is very high, so you can have the small deceleration area that couldn't compensate the acceleration area and the system will be unstable. Is it clear?
Yes, doctor. Thank you. Thank you.
Okay. Initially, the operating point was A, and the rotor angle is delta 0, where BM1 equal to BE. Hence, this point is steady state operating point. The acceleration area, acceleration power here equal to 0. And again, finally, the operating point is B, this point, finally, finally means after the oscillation, and this is the steady state operating point after the disturbance. Finally, the system will settle here at this point, where we have B mechanical equal to B electrical. This is B electrical and this is B mechanical. So they are equal here, and this is the steady state point. So point B is, and the rotor angle equal to delta S, which is B mechanical 2 equal to B electrical, and the acceleration power at this operating point is 0, and a steady state operating point. Okay. The BE cannot change instantaneously. Electrical power cannot change instantaneously. Hence, the difference B mechanical 2 minus B electrical equal to B acceleration will start accelerating the, and when we have this B mechanical sudden change, then the power, the electrical power will start to increases as such. But when we have here, as I mentioned, due to the inertia, the system will continue. But once it's continue, B electrical becomes greater than B mechanical, and this becomes a deceleration. So it will come back and forth, until it will, settle down at this point. Okay, as delta becomes greater than delta S, BE becomes greater than B mechanical, and then the rotor starts decelerating. This will continue until delta reaches delta M, until you have this one, and then the system becomes back. Delta starts decreasing and oscillating around B until it finally reaches the new steady state angle or steady state operating point at delta S. Okay, now the excess energy stored in the inertia during the acceleration, which is A1, and the deceleration is A2. So we can calculate A1 and A2. Can you, for net energy and for stability, this is the stability condition, and the net energy to be 0, and the acceleration is equal to the deceleration. So the net energy to be 0, A1 must equal to A2. And of course, you can calculate A1 rectangular, this rectangular minus the angle under the area under the curve, and also for A2, the area under the curve minus the area of this rectangle. So in this case, you can mathematically, you can this is multiply 2 over m. There are some, manipulation of these, and we need to then this is the derivation of the condition for the system to be stable in A1 equal to A2. And I would like to skip this this part. So we will end up with A1 equal to A2, and this is A1, which is a rectangular area, which is BM2 minus times this, minus the area under the curve from delta 0 to delta S. So this is A1, acceleration area. And this is a deceleration area. The area under the curve from delta S to delta M, this is the electrical power minus the rectangular area of B mechanical 2 times delta M minus delta S. So you equate these two equations together. Delta 0 equal to this, of course, delta and delta S also is known. Evaluating the integrals and substituting then you end up with this equation. So this equation is a function of delta M. B max is known, VM2 is known, delta M is unknown, delta M is unknown, delta 0 is known, all this are known. So the only unknown in this equation is delta M when you have this ones. Okay? So we need to solve this delta M, and we need to compare delta M versus delta max. They are 180 minus delta S in order to see whether the system is stable or not. If delta M is less, that means we have enough deceleration area to compensate the acceleration. If delta M is greater, that means no, the deceleration area is not enough to compensate. So of course you can, this is nonlinear algebraic equation. You can solve it either by trial and error, or you can solve it by iterative technique. It is nonlinear algebraic equation, so you can use Newton-Raphson method or Gauss-Seidel method to solve this algebraic equation. It is not a differential equation, so it is algebraic equation, so you can solve it, or you solve it by trial and error. So although delta is in degrees in B delta curve, in all equations involved, the derivation of the angles are in radian. Of course, when you solve this equation, all these angles will be in radian, must be in radian. And we cannot say no, this angle is in degree or this degree. All angles in radian. Deltas are in radian. So you solve, you get delta M in radian and so on. So the maximum value of delta M for stability is delta max, which is 180 minus delta S. The operation where, okay, if the operation were at the linear portion, of course, if you look at this curve, since we will solve by trial and error, if you solve by trial and error, you need to start with an angle and then you start improving the solution until you end up with the final one. So how to start? What is delta M initial value that you want to start with to solve this algebraic equation? Which value? And you have delta 0 known, delta S is known. Now we need to guess what is delta M, and we substitute in that equation, and we see whether the right hand side equal to the left hand side or not, and then we move right and left until we end up with the right hand side of that equation equal to the left hand side. So how to start with delta M? Is there a wise start for this delta M? You can start wisely. You can say, no, usually the system is operating in the linear part of the sinusoidal waveform. And assume that we can approximate this as a linear. So in this case, we expect in the delta M will be equal to delta S plus this. And then, of course, you have here two triangles here. And if this is linear, to have the area equal, so this will be equal to this one. So delta M as initial, we can start with delta S plus delta S minus delta 0. So yani 2 delta S minus delta 0. This is the wise start when you go to the trial and error solution. So this is the initial guess of delta M that you can start with. So this is the point that is given here. You know, if the operation were at the linear portion of the B delta curve, then A1 equal to A2 and the delta M equal to 2 delta S minus delta 0. So hence the selection of the first trial of delta M can be made wisely. Okay, so time is over. We expect a quiz today. Nobody remind me about the quiz. Okay, so let us keep it to next class. Do you have any question?
No question, Doctor.
Okay. If there is no question, so you can leave the meeting. We have Ayub Al-Harani, please.